Okay, thanks. So it's gonna be, I have no experimental data. This is gonna be pure theory, which is not my field. So in front of this august crowd of people, I hope to get feedback to improve my theory skills. So what's the point of this paper? So we know that rational learning and behavior does not easily fit observed data. There's decades and decades of experimental evidence and, let's say, stock market data and other stuff. We just see it's hard to fit everything we see in the world with pure rational learning. You obviously can. I can twist the environment in any way. We know there's essentially equivalences, but it's hard to do. Typically, so prior to the last 5 or 10 years, all of these gaps between data and model are explained with ad hoc models. So what I mean is that think of Hong and Stein. It's a very specific, they say, here's the DGP of news coming out. There's news watchers, there's momentum traders, and I tell you everything about everything in the world. So the news watchers and momentum traders, their specification of beliefs and actions are exactly well defined in that context of the paper. But suppose I slightly change the structure of how information comes out, the model, the exact literal modeling assumptions in that paper don't map into a new stochastic setting. And the same thing with more recent papers in microstructure, stuff like Kyle, where most of the literature prior to about 10 years ago is specific model designed for the purpose of explaining a specific empirical phenomenon. So that's very useful, but the difficulty is it's hard to evaluate these models in different stochastic contexts, and it's hard to use them. I can read Hong and Stein and understand it perfectly well, but say what can I take from that and apply to a different setting? I don't know. There's an art in that. So it's not easy to use their model in a different setting. So in 2013, Rabin had I think, Journal of Economic Perspectives, where he says he's pushing this research agenda about portable behavioral models. So portable extension of existing models should do a couple of things. They should extend existing rational models by formulating a modification that's embedded as a parameter value. So you have some psychological assumptions that come from psych theory. I want to make a concrete mathematical formulation of that that's embedded as some finite dimensional parameter. And that thing should nest the rational model. So some parameter value should be the rational model. What is the point of this? When you make it portable, it's well defined across domains. So it doesn't have to be a model that's only specific to Gaussian distributions. I can apply it to T distributions, maybe not analytically, but I could apply it and numerically evaluate integrals. Whereas a lot of the models, like for instance, think of Daniel Hirschleifer and Subramanian, that model is extremely specific to Gaussian and the information structure, where you have your own signal and there's a public signal. What if I change it to T distributions? That model has essentially no predictive power. So Rabin says those are useful for understanding the intuitive mechanisms that's going on, but you can't replace the rational paradigm with ad hoc models. You need a new paradigm that's as portable as rational expectations. So what's this paper? I'm going to start with Tversky and Kahneman's idea of the belief in the law of small numbers. And what does that mean? So from experimental evidence, it looks like people view a sample as similar to the population in all essential characteristics. This implies they're going to have exaggerated confidence in the validity of conclusions based on small samples. So I collect a small amount of data, I learn something about the world, I might learn too much, and I'm overconfident in what I've learned. So what is this paper? I'm going to take this psychological idea of the belief in the law of small numbers. I'm going to show you how you can completely mathematically embody this as a one parameter extension of Bayes' rule, which nests Bayes' rule as a specific parameter case. And because of this, it's going to be completely context agnostic. So I'm going to show you on the next slide is the functional form. I'm not going to specify any DGP at all. I'm just going to write Bayes' rule with an extra parameter to show a distortion. And it's going to capture things like base rate neglect, overconfidence, representativeness, overreaction to new information. And a key feature is that it's going to be nearly Bayesian. I'm going to show you that these distorted beliefs have a lot of rational properties. And essentially the only thing that it doesn't do that's rational is it overreacts. In every other way that you would think of all the fundamental properties of Bayesian learning, it satisfies Bayesian rationality. All right, so first, just a little bit of technical bookkeeping. We're going to have a sequence of nested information sets. T here is just an index. It doesn't have to represent any kind of cardinal time. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's just an ordinal index. We're going to define little I to be the increments to the information sets. So you can think of this as data. And delta is some random quantity. You could think of, in a Bayesian world, you could think of this as a parameter. You could think of this as a latent thing I'm trying to learn about. It's just something that's random that the agent is trying to learn about. It could be a parameter of a DTP. It could be a latent value in a Kalman filtering setting. And I'm going to show you examples of both. All right, what's Bayes' rule? The posterior beliefs about delta are proportional to the prior times the likelihood. We all know that. What is this distortion here? It's going to be exaggerated likelihoods. So when I put the colon B, that means Bayesian. Colon E is going to be exaggerated likelihoods, just to keep these two beliefs distinct because they look the same. Exaggerated likelihoods is going to look the same. Posterior is proportional to prior times likelihood. The only difference is the agent uses the wrong likelihoods. The agent uses the distorted likelihood, which is equal to the true likelihood raised to the power 1 plus theta. And I'm going to think of theta being a positive number. So theta bigger than 0 is going to capture exaggeration or overreaction. And theta between -1 and 0 is going to capture kind of conservatism or understating. So this functional form was actually introduced after I wrote this paper. I was doing a lit review and I found there's a 1980 QGE paper by Grether. It was a psychologist. It's amazing that in 1980, the QGE published a psych paper essentially. He wrote this functional form down as a reduced form description of psychological experimental data. So we already know this functional form fits field data because that's how Grether published in 1980 QGE. So I'm not going to justify this empirically as fitting. There's a published paper that tells you this fits empirical data on beliefs. But let's understand this a little bit more. I can rearrange this. I can rearrange Bayes' rule in terms of odds ratios. So we know that the log posterior odds ratio equals the log prior odds ratio plus the log likelihood ratio. With exaggerated likelihoods, it looks the same, except the log likelihood ratio is multiplied times 1 plus theta. So in odds form, in log odds forms, learning is an additive process. You just add the log likelihood ratio to what you believed before. Here, you're just adding too much. So whatever you added, you're going to add too much. You can immediately see that looks like an overreaction. Okay, now we want to understand this. So we have this functional form. It looks kind of cool, in my opinion. Let's understand it more deeply. I think that's the contribution of this paper. Okay, first, so let me preview some results. So this functional form, because of its exponential structure, it's really analytically useful in a variety of settings. So for example, when you have the exponential family and you have conjugate priors, all those conjugate relationships are preserved. Like I said before, it's going to preserve many rational properties of Bayesian learning. And I'm going to show you at the very end, the last couple of slides, it's going to look superficially like Diagnostic Expectations, which has been, Schleifer and co-authors have been developing this for about 10 years. It's going to contain the same kernel of truth idea, but the dynamics are going to be very different. So in a static setting, it's going to be almost identical to DE, but in a dynamic setting, it's going to be completely different. That's what I'll show you. All right, so how is this the law of small numbers? So think about a Popperian doing experiments. Like consider running the same experiment twice. I'm going to do some kind of titer and I'm going to measure something. I'm going to do some measurement. So I'm going to have two independent measurements of the same thing. I'm going to observe some random quantity X. And just suppose by pure accident that the realization of the first experiment is equal to the realization of the second experiment. So what is the joint likelihood of these two data observations? Well, since they're independent, the joint likelihood is the product of the marginals. But since x1 equals x2, it's just f of x1 squared. Okay, so this is the likelihood you're going to use to do Bayes updating. Think of exaggerated likelihoods. An agent who has a theta equal to 1, after he sees just x1, he's going to use the likelihood, but he's going to raise it to the 1 plus theta power, which is f of x1 squared. So this is the law of small numbers. He sees one observation. He treats it as if he ran the same experiment twice and accidentally got the same outcome. So you can see this embodies exactly the law of small numbers. I had one observation. I'm going to learn as if it were two observations that happen to have the same value. Okay, and you can actually do this a little bit more nicely in the exponential family. So take this whole exponential family that includes every distribution we ever use. Discrete distributions like Bernoulli and multinomial and Poisson. It includes Laplace and Wishart, normal. Every distribution it doesn't include T, but it includes lots of distributions. So in canonical form, the exponential family has a structure like this. X is the data, eta is the parameter, T is the sufficient statistic. Think of collecting n IID observations from some member of this exponential family. The joint likelihood is expressed like this, where T bar is the average sufficient statistic evaluated across all of my observations. What does exaggerated likelihoods do? Well, I'm going to raise this to the 1 plus theta power, but raising an exponential to the 1 plus theta power, I can pull the 1 plus theta into the exponential. The distorted likelihood has the same form as the correct rational likelihood, except there's a 1 plus theta multiplying out here. So it looks like where n is number of observations, I just multiply that times 1 plus theta. So this is literally, if I had 10 observations and theta is 0.3, I'm treating it as if I learned from 13 observations with the same sufficient statistic. So again, this shows you this is the law of small numbers. The thing I'm going to learn from is T bar, the average sufficient statistic. How many observations did I collect to obtain this sufficient statistic? It's actually n, but I treat it as if it's n times the 1 plus theta, which is bigger than n. Okay, so it's nearly rational. Let me just quickly give you a couple of properties. Because of this exponential structure, when you take the log of the distorted likelihood, it's 1 plus theta times the log of the correct likelihood, and you find the argmax of this, it doesn't change. So if you completely ignore your prior, suppose you had a perfectly flat prior and say, what's your belief? It's going to be the same as the rational person because you're just going to use the MLE. So this agent, when they have no prior information, is going to have the same beliefs as the rational agent. But it has a couple of other nice rational properties. First, the way the structure is set up, there's no forgetting. There's no implicit forgetting as a result of the passage of time. So if literal cardinal time passes, beliefs don't change unless there's new information. That's consistent with Bayesian learning. It has a property of independence of irrelevant information. What does that mean? It means that if you're trying to learn about GDP and I tell you that my shirt is blue, your beliefs about GDP don't change at all. And that's going to be important because this is not going to be satisfied by diagnostic expectations. It satisfies commutativity, which is the Bayesian property. So the order of receiving your data is irrelevant. If there's going to run 2 experiments, if I tell you the result of experiment 1 and then the result of experiment 2, or I tell you the reverse order, after I've told you both pieces of information, you're going to have the same final beliefs. So Bayesian learning satisfies commutativity, and so does exaggerated likelihoods. It also satisfies accumulation, which is really similar. The proof is the same. Accumulation means I can give you information in sequence and ask what are your final beliefs, or I can collect all of those experiments and give you a data dump and say, here's all the data from all the experiments. What are your final beliefs? Under Bayesian learning, the final beliefs are the same, whether I give you sequential information or a data dump. Under exaggerated likelihoods, it also satisfies this. Okay, so I'm going to define learning. So let's take 2 simple hypotheses. So delta 0 and delta 1 are 2 models of the world. Learning is going to be the impact of evidence on the beliefs. It's going to be the difference between the log posterior odds and log prior odds. So learning at time t, of course, implicitly this depends on the information at time t, the increment. Learning for hypothesis 1, hypothesis 0, with some learning rule omega, is going to be the difference between the log posterior odds and log prior odds. And this functional form, Good is a kind of a Bayesian epistemologist. He calls this the weight of the evidence in favor of delta 1 relative to delta 0. So under Bayesian learning, under Bayesian beliefs, this definition of learning is literally just the log odds ratio, the log likelihood ratio. So once we have learning and a learning rule, I'm gonna define overreaction. So for all hypotheses, delta 0, delta 1, and information, I'm going to say this learning rule omega exhibits overreaction. If in words rather than in math, learning should have the same sign as Bayesian learning, but greater magnitude. So if Bayesian learning is 0, if the Bayesian agent learned nothing, this agent learns nothing. If the Bayesian learned a positive number, this agent learns a positive number with a bigger magnitude. If the agent's learning is negative, the Bayesian agent's learning is negative, this agent's learning is negative with a greater magnitude. So this is my definition of overreaction. You react in the same direction as the Bayesian agent, but with greater magnitude. Okay, so here's the theorem, the main theorem of the paper. So exaggerated likelihoods, this functional form I've given you, it's the unique learning rule. So take any arbitrary learning rule, which is really just a stochastic process of belief, right? I have beliefs at time t, beliefs at time t plus 1. The stochastic evolution of that we call learning. So among all learning rules, which are Markovian, what does Markovian mean? It means that today's beliefs only depend on yesterday's beliefs and whatever data I've seen. It doesn't depend on, so yesterday's beliefs are sufficient for summarizing everything in the past, and today's information is today's information. So Markovian is, today's beliefs are a function of just those 2 things. Notice Markovian doesn't mean rational. Suppose I always believe it's going to rain today no matter what. That's Markovian, because my beliefs don't depend on anything in the past. It's just, I always believe there's a 100% chance of rain. So you can be arbitrarily stupid and still be Markovian. If the beliefs are also non-dogmatic, what does non-dogmatic mean? It really just means that the support of the biased beliefs are the same as the support of the rational beliefs. And you need this essentially, when you want to take this to asset pricing, that's going to rule out arbitrage. Why? Because if Valentin thinks that an event has 0 probability and I think it has probability 1, he's willing to sell me an option on that event at 0 price. And I'm willing to buy it at some arbitrary price. So one of us is wrong, which means there's an arbitrary under the objective measure, right? So we want objective and subjective beliefs to have the same support. Another way mathematically to say that is a Redon-Nikodym derivative exists. Finally, this thing should satisfy accumulation. Accumulation means, again, if I get my information in sequence or I get it as a data dump, my beliefs are the same. So if you also wanted to exhibit overreaction, exaggerated likelihoods is the only learning rule, which is Markovian, non-dogmatic, satisfies accumulation and exhibits overreaction. So in that sense, it's the minimal departure from rationality that generates overreaction. So rather, Grether wrote this as a reduced form description of experimental data, but we can derive this as saying, let's start with rationality and tweak one thing. We're going to make one tiny irrationality that you're going to overreact. In all other properties of Bayesian, you satisfy all the other Bayesian properties that we can derive of Bayesian. Let's do some examples. So first, I'm just going to show you that that gives you the representativeness heuristic. So suppose that we have Irish people and non-Irish people. Irish people, P fraction has red hair, which is bigger than Q, which is the fraction of non-Irish people who have red hair. I fraction of the world population is Irish. Suppose I have a person in a box and I tell you this person's hair is red. What's the probability that the person is Irish, conditional on the hair being red? Well, you can solve Bayes' rule. So the posterior odds ratio is the prior odds ratio times the likelihood ratio. But now with the exaggerated likelihoods, it's to the 1 plus theta power. So P over Q is what Giannoli and Schleifer in the stereotype paper call the representativeness of red hair. So you're taking the representativeness and exaggerating it. So in this static setting, exaggerated likelihoods gives you exactly Giannoli and Schleifer representativeness heuristic. But we can take this in IID Gaussian setting. So let's say that we have IID data. The data conditional on the mean is normally distributed with mean mu and precision tau. The mean is drawn, the prior mean is drawn from normal with some prior mean mu 0 and some precision tau 0. Let's solve for beliefs. Beliefs have this nice recursive structure. The mean after observing T observations is the prior mean plus something that looks like a Kalman gain times a surprise. And the posterior precision has the natural form, except, see, I exaggerate the posterior precision. So I've collected T observations. I treat it like T times 1 plus theta observations. And I'm learning too much. This Kalman gain is too close to 1. So what does this do? So you're going to have overreaction to perceived new information. That's this Kalman gain is too big. And you're going to have overconfidence. Your posterior precision is going to be too big. How does this look like? I'm going to take this form and rearrange it. So the numerator is going to be how far distorted beliefs are from the prior. The denominator is how far rational beliefs are from the prior. In this simple setting, this actually is just a constant. So this ratio of how far away the beliefs are from the initial belief is a constant fraction. So we can just do a simulation and plot this. The black line is the rational belief over time, d mean. So I've subtracted off mu 0. The blue line is the exaggerated likelihood belief, also again d mean, subtracting off the prior mean. And you can see these are exactly proportional, but with a proportionality constant bigger than 1. So the exaggerated beliefs are further away from 0 because you've learned too much. Now, once you see the intuition of, in this model, the mu is, the actual mean of the DGP is constant. Got it, thanks, Tony. We can easily extend this to a dynamic Kalman filtering setting. So essentially you're going to take these equations and slightly modify them into a Kalman filter. So let's say there's an AR1 hidden state. So the underlying hidden state, you can think of this as latent technological growth. It follows a simple AR1. It's mean 0, but it doesn't matter. I just normalize it to mean 0 for simplicity. And the errors are normally distributed. So there's a slow moving, mean reverting, unobservable state of the world. We're going to collect observations. We have an observable signal. The simplest form is truth plus noise. So I observe the latent value with some error, and I'm trying to learn XT. This is exactly Kalman filtering in the very simplest case of an AR1. So the signal noise, and this noise is going to be mean 0 with some noise variance. What happens in this world? All of the Kalman filtering equations are essentially, you're going to solve for the Kalman filter, and under exaggerated likelihoods, you're going to do Bayes' rule correctly. it's going to look just like the Kalman filter, except in some places, you're going to stick a 1 plus theta into a few places. Just like in the static setting, where I have the mu is constant, you see I put a 1 plus theta here and 1 plus theta here. The exact same thing is going to show up in the Kalman setting. Okay, so just like with the fixed mu, when theta is bigger than 0, this is going to cause overreacting to perceived mu. The Kalman gain coefficient is going to be too big. It's going to be too close to 1. In this model, I can solve for belief errors. So mu tilde is going to be the posterior mean of the exaggerated likelihoods agent. Mu t is going to be the posterior mean of a rational agent. And so the difference between these is the bias. If you ask, what's your best guess? One person tells you mu tilde, one person tells you mu. The difference in that we call the bias. I can solve for the DGP of the bias under the rational belief. So under the objective measure, we can solve what's the DGP of the bias of the behavioral agent. It turns out the bias of the behavioral agent also follows an AR1. The persistence of the bias is less than the persistence of the underlying process. So inherits, phi is the persistence of x, so the bias inherits the persistence of x, but 1 minus the Kalman gain is a number less than 1. Why is the persistence less than phi? Because under rational beliefs, things are martingales, but under wrong beliefs, if I solve for if I'm a rational agent, I solve for what the dumb agent's beliefs are going to be, I can forecast his forecast errors. So I can forecast the surprise of the dumb agent. And because I can forecast the surprise, he mean reverts his surprises. I know he's going to be surprised in the direction that goes against his bias, so the bias mean reverts a little faster than the actual underlying process. So let's just do a simulation, do a scatter plot. So on the x-axis, this is the rational posterior mean. The y-axis is the bias. You can see it's not quite exactly a straight line, but in the simulation, it's quite close. In the static setting where the mean didn't change, we've got this exact proportionality. Here, where there's a time-varying mean, because x is the mean of y, right? Y equals x plus error. When x is moving around, you don't get an exact proportionality, but it's actually quite close. So intuitively, you say bias is proportional to belief, roughly speaking, in this setting. Now, the bias is going to have the same autocorrelation sign as the underlying process. Why is this important? When phi is positive, the bias is going to be a positively autocorrelated AR1. But imagine I have a process that bounces around that has a negative autocorrelation. So x, rather than being slow-moving and persistent, the magnitude of x could be slow-moving and persistent, but x might bounce around. In which case, this model is going to give you that the bias bounces around too. That's going to be very different from a model of like sticky expectations or extrapolative expectations. Because those are very reduced form. They're designed for processes that have a positive persistence. But when you have negative persistence, those are going to be super counterfactuals. Here, my agent knows that if x is positive today, it's likely to be negative tomorrow, and positive, negative, positive, negative. So if we want to take this to experimental data, the best way to test this versus other models, which I haven't done yet, would be to give people a process that we know bounces around and see whether the beliefs bounce around or whether they always stay positive or always negative. Okay, and I show in the paper, not here, that this generates recency bias in the sense that I can, in this AR1 setting, I can rewrite beliefs as a linear filter of all past observations and solve what are those linear filtering coefficients relative to the rational coefficients, and you're going to see an exaggeration. You're going to see recency bias. So the coefficients on recent y's are going to be too large compared to rational. The coefficients on y's far in the past are going to be too small relative to rational. All right, I have a couple minutes left. I want to talk about diagnostic expectations because this functional form looks very much like diagnostic expectations. It's going to be different. So in diagnostic expectations, this is based on the representative heuristic. So actually, in Uran's paper, the overreaction and macro forecast, you give a functional form, which is the latest evolution of that functional form. If you rearrange it, what you get is that the diagnostic posterior is proportional to the rational prior times the likelihood. So this first term is the Bayes posterior, but then it's times this representativeness term. So at times, it's the actual likelihood of the data divided by the likelihood of a benchmark outcome raised to the theta power, the theta distortion. And just as an aside, so this benchmark is usually defined in their papers as the conditional expectation of the data, either with 1 lag or 3 lags or 3 years of lags. If IT does not have convex support, this benchmark might not even exist, because think of a discrete distribution. The mean might be 1.5 for a counting distribution, but 1.5 is not an outcome that can ever occur, so the likelihood of that is 0. So you have to be careful applying this to discrete distributions, but let's pretend everything is continuous, and so diagnostic expectations is well defined. So recall exaggerated likelihoods. The distorted posterior is proportional to the distorted prior times likelihood to the 1 plus theta. So the two key differences here are, I'm going to just say DE and EL because otherwise I'm going to get tongue-tied. In DE, you use the rational prior. In EL, you use the distorted prior. That's the main difference. The other small difference is in DE, this gets rescaled by the benchmark. That's going to be minor. This is going to only affect things like precision. But the key difference is going to be using the rational prior here versus the distorted prior here. Why does this matter? Because in general, DE beliefs are not persistent. So suppose you take this AR1 IID homoscedastic Kalman filtering setting, and you use the standard specification of the benchmark, where the benchmark equals the prior expectation of the data. In this case, the belief errors in diagnostic expectations are going to be IID and homoscedastic. So there's zero persistence in belief errors in DE. And this zero persistence actually contradicts Bordallo, generally Laporta, and Schleifer's in the paper Diagnostic Expectations of Stock Returns. They empirically measure this with stock analyst forecasts and look at the persistence of bias of analysts' long-term forecasts, and they find persistence which is contrary to the simplest version of diagnostic expectations. Whereas EL naturally generates persistence of the beliefs, of the belief errors, where that persistence is endogenous. There's no extra persistence parameter. The only parameters are the actual DGP and the single theta distortion parameter, and you can solve endogenously for what is the persistence of belief errors. Finally, let's just go remember the diagnostic expectations equation. Diagnostic expectations does not ignore irrelevant information. So let's just look at that. So when you have irrelevant information, what does that mean? It means the likelihood is flat. It's a constant function of the parameter. So if the likelihood is a constant function of the parameter, this is a constant, this is a constant, so this whole thing is a constant. When I take my prior, multiply it times a constant, and then do the integral to renormalize it, the beliefs don't change. So under irrelevant information, the base posterior is just going to be the rational prior, but so is the diagnostic posterior. So let's think about this. So suppose I just showed you on Thursday, we saw the unemployment numbers. You're learning something about the state of the macroeconomy. 1 minute later, you look at my shirt. I tell you my shirt is blue. The likelihood of my shirt being blue conditional on the state of the macroeconomy is a flat function. Once I told you my shirt is blue, you immediately forgot all of your distorted beliefs about GDP. And so if you think that you're getting useful information periodically and useless information almost continuously, because we essentially have continuous processing of our environments. So if useful information is periodic and useless information is continuous, then essentially diagnostic expectations are distorted on a set of measure zero in time. Almost all the time you're going to be rational because almost all the time you see useless information. So I think that pushing models to deal with irrelevant information is quite important in models of memory where you have long-term and short-term memory, because I can totally manipulate your short-term memory by giving you useless signals. All right, so there's a little bit more in the paper, but not that much. So what I want to know from you guys is, what else would you like to know about EL versus other stuff? And perhaps what more applications would show the usefulness or lack thereof of this framework? So, I've written something that's fairly general and shown you a bunch of general properties, but would you like to see this embedded into a model of investment? And that's going to give you, maybe firms are learning about their demand that's slow moving. If they see a positive demand shock, they overlearn, they might overinvest and so on. But where would this be useful in a finance context? Thanks so much.